Hey everyone, welcome back to Chem Story. Today, we're diving into chemical kinetics in organic chemistry. We're going to look at how reaction rates work, what factors can change those rates, and how we figure out the reaction order. By the end of this lesson, you'll know how to analyze reaction rates, and even predict how fast a reaction will happen. All right, let's get started. So, what exactly is chemical kinetics? Simply put, it's the study of reaction rates, how fast reactants turn into products. And this matters because it helps us understand how reactions actually happen, step by step. It also shows us how different factors, like concentration or temperature, can speed up or slow down a reaction. By looking at reaction rates, we're not just focused on the final result, we're digging into the entire process behind it. That's why kinetics is such a big deal in organic chemistry. The rate equation describes how the reaction rate depends on the concentration of the reactants. In other words, it tells us how fast the reaction changes as the concentrations change. You can see the equation on the screen, and it's actually pretty straightforward. The key idea here is that reaction rate depends on concentration, but it's not always a simple one-to-one relationship. The rate equation shows that the rate is proportional to the concentration of each reactant, but each one is raised to a specific exponent. Those exponents are called reaction orders, and they tell us how strongly each reactant affects the rate. Now here's something really important. Reaction orders don't always match the coefficients you see in a balanced chemical equation. You can't just read them off the formula. You have to determine them experimentally. That means two reactions might look almost identical on paper, but have completely different rate laws in practice. Another key concept is the rate constant K. Now, unlike reactant concentration, K doesn't change during the reaction. For a specific reaction at a specific temperature, it stays constant, but it does depend on temperature. That's where the Arrhenius Equation comes in. It explains how temperature and activation energy affect the reaction rate and how they're connected to that constant K. Now that we understand the rate equation, let's take a closer look at one really important idea, reaction order. Reaction order tells us how sensitive the reaction rate is to changes in reactant concentration. But this relationship isn't always straightforward. Different reactions respond to concentration changes in different ways, and reaction order helps us make sense of those differences. In the rate equation, the exponents A and B represent the reaction order for each reactant. For example, if a reaction involves reactant A, then its effect on the rate depends on the exponent A. That means it's a reaction of order A with respect to A. Same goes for reactant B. It follows a reaction of order B, and if you add those together, the overall reaction order is just A plus B. Let's go through some examples to make this even clearer. First, let's talk about zero-order reactions. These are pretty unique because the reaction rate doesn't change at all, no matter how much reactant you add. If you look at the graph, you'll see a flat line. That means increasing the concentration has zero effect on the rate. This usually happens when a catalyst or surface is already saturated. So even if you add more reactant, there's just no place for it to go, and the reaction doesn't speed up. Next, let's look at first-order reactions. In this case, the reaction rate is directly proportional to the concentration of a reactant. So if you double the concentration, the rate doubles too. If you check out the graph, you'll see a straight line relationship. More reactant means a faster reaction, and the increase happens at a constant rate. Finally, let's talk about second-order reactions. These are even more sensitive to concentration changes. As the concentration goes up, the reaction rate increases, but not just steadily, it goes up exponentially. If you look at the graph, you'll see the curve bending upward, which means even a small increase in concentration can cause a much bigger jump in reaction rate. One important thing to remember is this. When a reaction involves multiple reactants, the order for each reactant has to be determined experimentally. Once we have those values, their sum gives us the overall reaction order. Here's something a lot of people get wrong. You can't predict the rate equation just by looking at the balanced chemical equation. Even reactions that look almost identical on paper can have completely different rate laws in real life. That's why reaction orders must always be found through experiments. And understanding reaction order isn't just about putting reactions into categories. It actually helps us predict and control reaction rates in everything from lab research to real industrial processes. One of the most important factors that affect reaction rate is temperature. Even a small increase in temperature can make a reaction go a lot faster. But why does that happen? The answer lies in the Arrhenius equation. You can see the formula on the screen, but instead of breaking it down, let's focus on what it really means in organic chemistry. We're talking about how temperature affects reaction rates, and why that actually matters when we study organic reactions. Before we dive in, let's quickly touch on something essential: activation energy, or EA. We won't go into the math just yet, but this concept is key when it comes to understanding organic reactions. Activation energy helps explain why some reactions are fast, while others are painfully slow. It's a big part of understanding reaction mechanisms and figuring out how to optimize reaction conditions. So what is it exactly? Simply put, activation energy is the minimum amount of energy needed for a reaction to happen. It acts like a barrier that molecules have to overcome. If they don't have enough energy, they'll bump into each other, but they won't actually react. Now, let's see how that connects to temperature and how it affects the speed of a reaction. We know that increasing temperature speeds up reactions, but why does that happen at the molecular level? Well, every reaction has a rate constant, K, and that constant tells us how fast the reaction proceeds. But here's the important part: K isn't actually fixed. It changes depending on the temperature. The Arrhenius equation explains that relationship. As the temperature goes up, K increases too, and that means the reaction speeds up. At the molecular level, reactions happen when molecules collide with enough energy to overcome the activation energy barrier, EA. But here's the thing: not every collision leads to a reaction. Only the ones with enough energy actually result in a successful reaction. So why does higher temperature make reactions faster? It's because higher temperatures increase the number of successful collisions. As temperature goes up, more molecules gain enough energy to get over that EA barrier. That means a larger fraction of collisions actually turn into reactions. And that's the real reason why higher temperatures speed things up: more energetic molecules, more successful collisions, faster reactions. In this graph, the x-axis represents collision energy, and the y-axis shows the fraction of molecules that have that energy. As temperature increases, the entire distribution shifts to the right, which means more molecules now have enough energy to overcome the activation energy barrier, EA. Now, take a look at the graph. You'll see two curves, one for T1 and one for T2. T2 represents a higher temperature. At the lower temperature, T1, most molecules don't have enough energy to reach EA, so only a small fraction of the collisions actually lead to a reaction. But at the higher temperature, T2, a lot more molecules exceed that EA threshold. That means more successful collisions and a faster reaction overall. This is exactly why raising the temperature speeds things up. More molecules have the energy they need to react. And this applies whether the reaction is exothermic or endothermic. It doesn't matter if the reaction releases heat or absorbs it, the same idea holds. So the key takeaway is simple: higher temperature means a faster reaction, and that's all because more molecules have enough energy to overcome the activation energy barrier. So far, we've talked about activation energy and how it affects reaction rates. Now let's see how catalysts fit into the picture. A catalyst is a substance that speeds up or sometimes slows down a reaction by changing the activation energy. What's interesting is that the catalyst itself isn't used up in the reaction, but it still plays a huge role in how fast the reaction happens. A positive catalyst, which is what we usually mean when we say catalyst, works by lowering the activation energy, EA. And when EA is lower, more molecules have enough energy to react. That means more successful collisions and a faster reaction overall. Take a look at the graph. The curve shows different energy barriers for the same reaction. Without a catalyst, the activation energy, EA, is relatively high, so only a small number of molecules have enough energy to react. But with a positive catalyst, the energy barrier is lower. That makes it much easier for more molecules to successfully collide and react. And this is exactly why catalysts are so widely used, both in industrial processes and in biological systems. They help reactions happen faster without being used up themselves. A negative catalyst, also called an inhibitor, does the exact opposite of a catalyst. It raises the activation energy, which makes it harder for molecules to react. And when that happens, fewer collisions have enough energy to succeed, so the reaction slows down. Looking at the graph again, you can see that when a negative catalyst is present, the activation energy is actually higher than in the uncatalyzed reaction. That means fewer molecules have enough energy to react, and as a result, the reaction slows down. Negative catalysts are useful when we want to control a reaction and prevent unwanted effects like food spoilage or oxidation. Now, to summarize, catalysts don't change the overall reaction itself. They only control how fast the system reaches equilibrium. A positive catalyst speeds things up by lowering EA. A negative catalyst slows things down by increasing EA. Now, let's take one last look at the graph. Without a catalyst, only the molecules in region B and C have enough energy to react. But when a positive catalyst is added, even the molecules in region A can now participate, and that boosts the reaction rate. On the other hand, a negative catalyst raises the activation energy, so now only the molecules in region C can react, which means way fewer reactions actually happen. This is why catalysts are so powerful. They don't change the reaction itself, but by adjusting the activation energy, they can dramatically affect how fast the reaction takes place. All right, that wraps up our lesson on reaction kinetics and catalysts. We've explored how temperature affects reaction rate, what activation energy really means, and how catalysts can either speed up or slow down a reaction by changing the energy barrier. Understanding these ideas is key to mastering organic chemistry, whether you're analyzing reaction mechanisms or optimizing lab conditions. If you found this lesson helpful, don't forget to like, subscribe, and hit that notification bell so you don't miss the next video. Thanks for watching, and I'll see you in the next one.